Last session, we have discussed basic properties of Laplace transforms, followed by classroom workbook on Laplace transforms. Now, in this session, we discuss inverse Laplace transforms. So, Laplace transform and its inverse. They are just like a derivative and integration. See, when you try to find the integral of a function, suppose when integral f of x dx is g of x, what does it mean? Derivative of g of x is f of x. I will write on the board. Suppose if integral f of x dx equal to g of x, what does it mean? Derivative of g of x is f of x. In the same way, we can easily find inverse Laplace transform of any function. Suppose if a function f of t is given, generally we used to find its Laplace transform in terms of the signal variable s. Now it's reverse operation. So f of s will be given. That means the Laplace transform of a function is given. You need to find its inverse Laplace transform, that is f of t. So earlier we have solved problems like this. Small f of t is given, we need to find its Laplace transform. Now it's a reverse operation. Instead of given function, they used to give its Laplace transform. We need to find a function for which this is the Laplace transform. So basically this is called reverse of previous operation, just like derivatives and integration. Okay. Now let us discuss at first the definition of inverse Laplace transform. Suppose if L of f of t, L of small f of t equal to capital F of s, then L inverse of f of s equal to small f of t. So inverse Laplace transform is denoted by L inverse. You take this LHS L to the right hand side, it becomes inverse operator. So this is Laplace operator, this is its inverse operator. If the Laplace transform of f of t is capital F of s, then L inverse of f of s is given by f of t. We can discuss some properties. L inverse of a into f of s plus or minus b into g of s. Actually, this is the Laplace transform of small f of t, and this is the Laplace of small g of t. So therefore, this can be written as a into L inverse of capital F of s. If it is plus, we get plus. If it is minus, we get minus, plus or minus b into L inverse of g of s. L inverse of g of s. This is true for all constants a comma b, and this is called linear property for inverse Laplace transforms. Earlier we have seen this property for Laplace transforms. Again the same property works even for inverse Laplace also. Now L inverse of, for example, 1 by s square plus a square. If it is a, this becomes sin at. So this can be written as L inverse of, this is 1 by a into a by s square plus a square. So constants can be manipulated like this. So therefore this is 1 by a into this is sin at. In the same way you can find inverse Laplace of this one. This is s by s square plus a square. This is nothing but cos at. Now suppose if I have L inverse of 1 by s power n, 1 by s power n. So this can be written as L inverse of 1 by s power n minus 1 plus 1. So it is in the form s power n plus 1. So here n minus 1 factorial is required. So manipulate with n minus 1 factorial and divide with 1 by n minus 1 factorial, because constants can be manipulated. Now this n minus 1 is called as n value. So this is nothing but 1 by n minus 1 factorial into, and this is nothing but Laplace transform of t power n. So this is the way you get inverse Laplace of any function. We have many properties like shifting properties, change of scale property. All the things will work here also. Okay. So we can easily manage inverse Laplace transforms once Laplace transform is very clear to you. Okay. Or when you go through Laplace transforms, inverse Laplace transforms, just give the priority at first for Laplace transform. So everything is based on formulae followed by various properties. If Laplace transform concept is very clear, I think it's not a big issue. So handling inverse Laplace is very simple. Okay. So first write this definition. If L of f of t equal to capital F of s, if L of f of t equal to capital F of s, then L inverse of f of s, then L inverse of f of s equal to small f of t, small f of t. After that you can write these points. This is actually t power n minus 1 because Laplace of t power n minus 1 is, this is t power n plus 1. So you will get this as t power n plus 1. Yes, this is n only. T power n only because Laplace of t power n is this one s power t power s power n minus 1 factorial by this one. So this is exactly t power n. Now let us try to find inverse Laplace transforms of few functions based on partial fraction expansions. Okay, based on partial fraction expansions. Let me recall the previous formula. I think there is some calculation issues. Let us see. Previous one is the last one we managed with this. I think this is inverse Laplace of this one is inverse Laplace of previous cases. This one 1 by s power n plus this is 1 by s power n. So this we can write it as inverse Laplace of 1 by s power n minus 1 plus 1. So here this is n minus 1 is there. So we can divide with 1 by n minus 1 factorial into L inverse of n minus 1 factorial divided by s power n minus 1 plus 1. So therefore this is 1 by n minus 1 factorial into what is Laplace of t power n? This is n factorial by s power n plus 1. Yeah, it is actually n minus 1. So make this correction. This is actually t power n minus 1. Previous we wrote it t power n. This is t power n minus 1. Make a correction in the previous case. So therefore this is replaced by, actually earlier we wrote t power n. This is exactly t power n minus 1 because n is nothing but n minus 1. So 1 by n minus 1 factorial into t power n minus 1. Now let us find inverse Laplace transforms using partial fractions. Inverse Laplace transform using partial fractions. This is one of the important model. We start with some basic examples. Suppose we need to find inverse Laplace transform of 1 by s into s plus 4. I need to find inverse Laplace of this. Now this can be written as L inverse of 1 by s minus 1 by s plus 4. But when you simplify this, you will get 4 extra in the numerator. So here it is 1 only. So therefore this can be divided with 1 by 4. Therefore this 1 by s into s plus 4 can be written as 1 by 4 into 1 by s minus 1 by s plus 4. Now between functions of s we have minus. So we can apply linear property. This is 1 by 4 into L inverse of 1 by s minus L inverse of 1 by this s plus 4. I can write it as s minus of minus 4. So 1 by 4 into, for which function Laplace transform is 1 by s? 1. So L inverse of 1 by s is 1. This is in the form L inverse of 1 by s minus a value minus 4. And this is the Laplace of e power minus 4t. Therefore, the result is 1 by 4 into 1 minus e power minus 4t. So this is a simple function in terms of x. So we got this using partial fractions. So this is one of the example. Note this point. Now let us go to example 2. Let us find L inverse of 1 by s plus 2 into s minus 9. So I need to find Laplace of this transformation, inverse Laplace of this. So let us go for partial fraction. Here the power of s is 0. Here the power of s is s square. So we can take like this. Let 1 by s plus 2 into s minus 9. This can be written like this. A by s plus 2 plus b by s minus 9. Where a comma b are some constants. Now cross multiply this. We get 1 equal to a into s minus 9 plus b into s plus 2. Now my task is to get the values of a and b. Once I get values of a and b, I can replace here so that we got plus symbol, so that we can easily get the inverse Laplace of this as well as this. Now to get a value, take b equal to minus 2. Let s equal to minus 2. Then this quantity will be nullified. So this becomes 1 equal to minus 2 minus 9. So this is minus 11 into a. So the value of a is minus 1 by 11. This is the strategy to get a value. Similarly, to get b value, this must be nullified, so that I should take s value 9. So take s equal to 9. So this becomes 1 equal to, this is b into 11. So therefore the value of b is 1 by 11. So therefore we got a value minus 1 by 11, b value 1 by 11. Therefore I got a partial fraction expansion of 1 by s plus 2 into s minus 9. Now my task is very simple, to get its inverse Laplace transform. So therefore L inverse of 1 by s plus 2 into s minus 9. This is nothing but L inverse of, here the value of a is minus 1 by 11. So minus 1 by 11 divided by s plus 2, b is 1 by 11 divided by s minus 9. Now apply linear property. So in this case, this is minus 1 by 11 into L inverse of 1 by s plus 2 can be written as minus of minus 2 plus 1 by 11 into, this is L inverse of 1 divided by s minus 9. So this is minus 1 by 11 into, this is e power minus 2t plus 1 by 11 into, this is e power 9t. So this is 9, e power 9t. So therefore this is 1 by 11 into e power 9t minus e power minus 2t. So therefore the inverse Laplace of this function is this. So this is the way to get the constants a and b. This is very simple partial fraction expansion. Here the power of s is 2. When you simplify this, the power of s becomes 2. Here power of s is 0. So here degrees are 0 is less than or equal to 2. So in that case, we need to proceed in this way. A by s plus 2 plus b by s minus 9. So this is the way to get the values of a and b. Or you can compare both sides coefficient of s square. After that constants. So that is one way, and this is another simple way to get the constants a and b. Once I get constants a and b, my task is simple. Now we discuss one more example. Suppose I need to find inverse Laplace of s plus 1 divided by s minus 1 into, for example, s plus 2. I need to find inverse Laplace of this. Now here this is a rational expression. Here the power of s is 1. Here the power of highest power of s is 2. So here the power of s is 1. Here it is 2. 1 is less than or equal to 2. So therefore this can be written like this. S plus 1 by s minus 1 into s plus 2 equal to a by s minus 1 plus b by s plus 2. So cross multiply and cancels few terms. We get s plus 1 equal to a into s plus 2 plus b into s minus 1. Now to get a value, I will take s value 1. Suppose when you take s value 1, then this becomes 1 plus 1, 2. So this is 1 plus 2, 3, 3a. So a becomes 2 by 3. Similarly, to get b value, take s value minus 2. And s is minus 2. Minus 2 plus 1. Minus 1 equal to, this will be nullified. So this is minus 3b. So b equal to 1 divided by 3. So therefore, I got a value 2 by 3, b value 1 by 3. So therefore, this L inverse of this expression s plus 1 by s plus 1 into, so this is s minus 1. S plus 1 by s minus 1 into s plus 2 equal to L inverse of the value of a is 2 by 3. So this is 2 by 3 divided by s minus 1 plus b value 1 by 3 divided by 1 by s plus 2. So 2 by 3 you can take outside. L inverse of this e power t plus 1 by 3 into L inverse of 1 by s plus 2. Here a value is minus 2. Plus 2 can be written as minus of minus 2. So this becomes e power minus 2t. Therefore, 2 by 3 times e power t plus 1 by 3 into e power minus 2t. So this is the way we can get inverse Laplace transforms by using partial fractions. If some complicated functions are there, if it is very difficult to manage this by partial fractions, we can easily verify options, or even if we can handle them in the different way also. Now, in one of the previous sessions in chapter 6, we have discussed convolution theorem. So let me recon convolution theorem. The statement of convolution theorem is this: L of f of t star g of t equal to L of f of t dot L of g of t. So this is the statement of convolution theorem. Now when you take this L to the RHS, this becomes f of t star g of t equal to L inverse of L of f of t dot L of g of t. So therefore, the conclusion of convolution theorem is we can easily get inverse Laplace transform of product of two functions in the variable s. Because when you simplify this, you will get f of s. Actually, this is L of f of t. This is g of s. So therefore, when you want to find inverse Laplace of product of two functions in the variable s, then you apply its convolution product. So the basic advantage of convolution theorem is we can find inverse Laplace transform of product of two functions in the variable s. Note this point. Very, very important. Note. By using convolution theorem, one can find, by using convolution theorem, one can find the inverse Laplace transform of, by using convolution theorem, one can find the inverse Laplace transform of product of two functions in S. The product of two functions in S. Now our next task is to find inverse Laplace transforms using convolution theorem. So next concept. Inverse Laplace transforms using convolution theorem. Very, very important. Inverse Laplace transforms using convolution theorem. Now we start with one or two basic examples. Let us see, suppose I want to find L inverse of 1 by s into s plus 2. We can manage this by using partial fraction very simply, but let us try to handle this by using convolution theorem. So this can be written as L inverse of 1 by s into 1 by s plus 2. So this is L inverse of this 1 by s, I can write it as Laplace of 1. This 1 by s plus 2 is nothing but Laplace of e power minus 2t. So therefore this is L inverse of L of f of t, where f of t is constant function. This is L of g of t, where g of t is e power minus 2t. So according to convolution theorem, this becomes f of t star g of t. So according to convolution theorem, L inverse of L of f of t dot L of g of t is f of t star g of t. So here f of t is 1. G of t equal to e power minus 2t. So therefore its inverse Laplace is f of t star g of t. Now let us write convolution product definition. F of t star g of t. This is integral 0 to small t f of capital T into g of small t minus capital T dt. So this is integral 0 to t. It is a constant function, so f of capital T also 1. But this is g of t e power minus 2t. So small t is replaced by t minus capital T. So e power minus 2 into small t minus capital T dt. So in this integral, t is a variable, capital T, but small t is constant. So this e power minus 2t we can take before integral. So this is e power minus 2t into integral 0 to t. This becomes e power 2t dt. So therefore this is e power minus 2t into its integral is e power 2t by 2. Limits are from 0 to t. So therefore e power minus 2t by 2 into replace capital T by limits e power 2t minus e power 0 is 1. So therefore this is 1 by 2 into 1 minus of e power minus 2t. So this is the inverse Laplace transform of this function using convolution theorem. We can manage this very easily by using partial fraction expansion. So when you go to partial fraction expansion way, it's simply a two-line steps. L inverse of this 1 by s into s plus 2, I can write it like this: 1 by s minus 1 by s plus 2 multiply with 1 by 2. So therefore this becomes 1 by 2 into L inverse of 1 by s minus L inverse of 1 by s plus 2. So therefore this is 1 by 2 into L inverse of 1 by s1, L inverse of 1 by s plus 2 e power minus 2t. So just it is a 2 or 3 steps procedure. But the advantage of convolution theorem is we can get inverse Laplace transform of product of two functions in S, even though if it is very complicated. I will go for one complicated example which cannot be handled so easily by partial fraction expansion. See, when you handle this is very simple. So even if you can handle this by convolution theorem, but it may take some more time. So finally result will be same, 1 by 2 into 1 minus e power minus 2t. So it may take some 7 to 8 steps by using convolution theorem, but by using partial fraction it is simply a 1 or 2 lines procedure. But don't think that always partial fraction becomes very simple for all complicated functions. So when you are handling inverse Laplace of complicated functions in the variable s, this is so effective. Let me handle one more example after this. Okay. So for the time being, you note down these points. Now let us handle one complicated example. Suppose we want L inverse of s by s square plus 1 whole square. So for this partial fraction expansion may not be simple, very complicated. So let us handle this. This is L inverse of 1 by s square plus 1 into this is s by s square plus 1. So therefore this is L inverse of this 1 by s square plus 1 is L of sin t into this is L of cos t. So by convolution theorem statement, this is sin t star cos t. So therefore f of t is sin t, g of t is cos t. So by convolution this is integral 0 to t sin capital T into cos of t minus t dt. Now how to handle this? We have a dot. So one is sine function and this is cos function. If it is either plus or minus, we can manage the integration by splitting it. So here sin A dot this. So multiply with 2, divide with 2. So this becomes 1 by 2 into, this is in the form of 2 sin A cos B. So we have a formula for this 2 sin A cos B. This is sin of A plus B plus sin of A minus B. So here A value is, for example, capital T and B value is small t minus capital T. So 2 sin A cos B is sin of A plus B plus sin of A minus B. So expand like this. Then this becomes sin of A plus B. So capital T, capital minus T will be cancelled. This is sin T plus sin of this minus of this. You will get 2 capital T minus T. So this is anyhow integral 0 to T. This function is like this. Integral 0 to small t dt. Now here we are integrating this function with respect to dt. So therefore this small t is a constant. So sin t can be taken before integral. So therefore this value is nothing but 1 by 2 into sin t. So this can be taken before integral into. So this is integral 1 dt. This is t. Limits are from 0 to t plus integral sin is minus cos. So this is minus of cos 2t minus t divided by the derivative of this with respect to capital T is 2. Limits are from 0 to t. So like this. So therefore this becomes 1 by 2 into, replace capital T by t. This is sin t minus sin 0 0. This is minus 1 by 2 into, replace capital T by small t. So this is cos t and replace this by this. So this is minus of course this is actually t times sin t. You will get t sin t minus this is cos of minus t. But we know that cos is even function. So cos t is even function. Therefore cos of minus t is same as cos of plus t, that will be cancelled. So the result is half into t sin t. Therefore the inverse Laplace of this function is half of t sin t. This is actually 1 by s square plus 1 into s by s square plus 1. This is Laplace of sin t. This is Laplace of cos t. You can call it as f of t and this you can call it as g of t. So by convolution theorem, this is f of t star g of t. Apply convolution product definition. And here we got sin A cos B. Multiply with 2, divide with 2. When you are handling problems like this, multiply with 2, divide with 2. And apply functions, apply formula using sin of A plus B or sin of A minus B or cos A minus B, cos of A plus B. Depends on situation. So when two cos functions are there, you need to apply cos of A plus B, cos of A minus B. When two sin functions are there, same formula, cos of A plus B, cos of A minus B. But when one is sin, another is cos, you need to apply this formula, sin of A plus B and sin of A minus B, and simplify this, we are getting half into t sin t. So note this. Now the next concept is, we will try to solve linear differential equations with the constant coefficients using Laplace and inverse Laplace transforms. So next concept is solving differential equations using Laplace and inverse Laplace, using Laplace and inverse Laplace transforms. Solving differential equations using Laplace and inverse Laplace transforms. Let us start with an example. Suppose I have an equation like this. For example, d square y by dt square minus 4y equal to 0. Suppose the boundary conditions are like this. Y of 0 equal to 1. For example, y dash of 0 equal to 2. It is a second order homogeneous linear equation with the constant coefficients. Now I want to solve this equation. Here two boundary conditions are given. What is the importance of boundary conditions to get the constants C1 and C2? So it is a second order equation. When you find its general solution, we get two general constants C1 and C2. So to get those constants, two boundary conditions are given. Y of 0 is 1, y dash of 0 is 2. Now let us try to solve this equation by Laplace and inverse Laplace. So this is actually y double dash of t minus 4 into y of t equal to 0. Apply Laplace on both sides. L of y of t minus 4 into Laplace of y of t equal to Laplace of 0 is 0. We have applied Laplace on both sides. Y double dash t means second order derivative. Y is a function in terms of t, so in place of y, I wrote y of t. Apply Laplace on both sides and apply linear property. Laplace of y double dash of t, this is s square into y of s minus s into y of 0 minus y dash of 0. In previous sessions, we have explained how to find Laplace of derivative of a function, L of f for n of t. Here n value is 2. So s square into y of s minus s into y of 0 minus y dash of 0 minus this is 4 into L of y of t. This is y of s only equal to 0. Now here you group y of s terms, you will get s square minus 4 into y of s. Y of 0 is 1, y dash of 0 is 2. So this is minus s minus 2 equal to 0. Therefore, y of s equal to s minus 2 divided by this is s square minus 4. So therefore, let me check out this. Here y of 0 is 1. So this is n. Y dash of 0 is 2. So this is 1 s minus 2 into s plus 2. This is 1 by s plus 2. So here y of s we got it as 1 by s plus 2. Therefore, y of t is its inverse Laplace. So L inverse of y of s. So this is L inverse of 1 by s plus 2. So we are getting e power minus 2t. So therefore, when you try to do this, you will get this value. Y of t is e power minus 2t. Let me cross check out this. So this is y double dash of t minus 4 into y of t equal to 0. Apply Laplace on both sides. Even you can cross verify this. Y of 0, 1. When you find its derivative, we get, oh, this is actually 1 by s minus 2 into s plus 2. But when you find its derivative, we are getting minus 2. Minus 2 times e power minus 2, it must be 2. But let us see. So there is some calculation issue. S square into y of s minus s into y of 0 minus y dash of 0. Yeah, here it is. When you take this RHS, it becomes plus 2. Now this becomes 1 by s minus 2. So therefore this is 1 by s minus 2. Now it is 1 by s minus 2. So the result is e power 2t. Now you can easily check it. So y of 0, 1. Differentiate, you will get 2 times e power 2t. The condition is 2. So this is the way we can easily solve higher order linear equations with the constant coefficients using Laplace and inverse Laplace transforms. Note this. The session is over. Thank you so much.